Welcome to the next lecture on modulation techniques for mobile communications. The outline for today's talk is as follows. We will start with a brief recap of what we have learnt so far. We will then look at Emery quadrature amplitude modulation or QAM. We then go into PN sequences and look at some spread spectrum techniques. The first one will be direct sequence spread spectrum or DSSS. Then we will look at frequency hopped spread spectrum or FHSS. We will then evaluate the performance of direct sequence spread spectrum, followed by that of frequency hopped spread spectrum. We will look at the advantages and disadvantages of spread spectrum systems. So, this is the outline for today's talk. First, the recap. In the past couple of lectures, we have looked at linear digital modulation techniques. In specific, we have looked at the binary phase shift keying, the differential phase shift keying, the quadrature phase shift keying or QPSK. Within that, we looked at two variations. One was the offset QPSK and then the pi by 4 QPSK. These two were intended to ensure that phase changes are limited in the first case of offset QPSK to 90 degrees and in pi by 4 QPSK to 135 degrees. We then graduated to constant envelope modulation techniques. Specifically, we looked at binary frequency shift keying and two special cases, the minimum shift keying and the Gaussian minimum shift keying. We learnt how GMSK is generated and received, and it is used for GSM communication systems. Finally, we looked at Emery PSK systems. Now, today we will start where we left off last time with the quadrature amplitude modulation signals and then go on to study the spread spectrum techniques. What are Emery quadrature amplitude modulation techniques? First of all, it is a hybrid modulation technique. So far, we have either dealt with amplitude or phase variations. Here, we have for the first time both amplitude and phase variations in order to encode the data. The constellation diagram of a 16-array QAM consists of a square lattice of signal points. Let us see how it looks. Here in this slide, we have 16 points in the constellation diagram. Let us look at the axes. These are two orthogonal axes. Let us label them phi 1 and phi 2. This x axis could be cos omega ct, the y axis could be sin omega ct, or any two orthonormal functions. Each of the points here in the signal constellation represents one of the possible signals in the signal set. Now, what is interesting is each of the signals carry with it a label. There are 16 possible symbols and hence 4 bits per symbol can be assigned. Now, there are very many ways to assign 4 bits per symbol. Here we have done one particular method of encoding. This is called gray coding. The important feature of gray coding is that for any adjacent symbols in the signal set, the number of bits that change is only 1. That is, for example, if I consider this one where the bits mapped are 1011, then to the right of it we have a mapping 1010. Please note that the Hamming distance or the number of bits that are different here is only 1 at the last place. If you consider the symbol above, there again we have flipped only one of the bits and we come to 0011 and so on and so forth. On the left you have flipped the third bit only. So, the nearest change, the closest Euclidean distance wise symbol is also the closest Hamming distance wise separation. The logic is as follows: the probability of error increases as you move two signals closer to each other in the signal space. And so if the probability of error increases, and if error does happen, then the number of bits in error should be minimum, right? So if you consider two extreme points, consider for example this one and this one, the probability of these two being in error, that is you send this one and you interpret it as this one, is very, very low, though non-zero. Then almost all 4 bits need to be flipped, or at least 2 bits need to be flipped. So the number of bits changes, the Hamming distance is much larger for these two. This method is called gray coding, wherein you only change 1 bit at a time when you move from one signal to the nearest next symbol. The general form of an Emery-Quam signal can be defined as follows. Here, as you can see, I have the two axes cos 2 pi f c t and sin 2 pi f c t, and then these are the normalizing factors under root 2 E min over T s. I have AIs and BIs. Here I can vary from 1 through m, and these actually tell you where exactly on the x and the y axis your signal point is located. E min is the energy of the signal with the lowest amplitude. Please remember, from the constellation diagram, different signals are farther away from the origin differently. The closest ones pertain to the E min scenario. AIs and BIs are a pair of independent integer chosen according to the location of the particular signal point. In Emery-Quam, energy per symbol and also distance between possible symbol states is not a constant. Question?
Sir, is it necessary that m should be the power of 4?
Okay, the question being asked is, should m here in Emery-Quam be a power of 4? The answer is, if you are putting it in an xy coordinate, yes, it has to be either 4 or 16, but it is also found that you can have 32 quam, wherein it is not a perfect square lattice. So if you go back to the lattice, instead of having 16 points, if I put some off-centered points, then also it is my quam. Right? Traditionally, we will have 16 quam, 64 quam, but it is also possible to find 32 quam. So not necessarily that it has to be power of 4, but power of 2, yes, because we would like to have them in pairs, specifically when mapping the bits. So if it's 5 bits per symbol, then you will have 32 symbols, right? I cannot have 17 quam. I cannot map my bits. The signals SI may be expanded in terms of a pair of basis functions. These basis functions phi 1 and phi 2 are given as follows: cosine 2 pi f c t and sine 2 pi f c t normalized. The coordinates of the ith message point are AI under root E min and BI under root E min, and here, as you can see, I can label AIs and BIs in the form of a matrix. It's simply the definition of the location in the constellation space. Right? I have two axes, so I need an x location and a y location. For example, for m is equal to 16 quam, the L by L matrix looks simply like this. It tells me that the leftmost point is located at minus 3, 3, then minus 1, 3, and so on and so forth up to 3, minus 3. Now, let us talk about the average probability of error in an additive wide Gaussian noise channel. Clearly, there are some points in the constellation diagram which are closer to each other than other points. Certain pairs are closer to each other than other pairs of points. So those are the most likely points to be in error. The average probability of error is approximately 4 1 minus under root m q under root 2 e min over n naught. So here approximately the probability of error is given as a function of m for an Emery QAM. If you want to define it in terms of average signal energy, the probability of error expression comes out as follows. Now let us talk about power efficiency and bandwidth. As always, whenever you have to pick and choose a particular modulation scheme, you have to talk about the power efficiency, the bandwidth efficiency, and how simple or complex is it to implement it in transmitter and receiver. So these are the three factors which must be considered for any modulation scheme. The power efficiency of a QAM is superior to Emery PSK. The bandwidth efficiency of QAM is identical to Emery PSK. In fact, the moment you start going for higher modulation schemes, then you kind of switch to QAM. It's not wise to go beyond 16 PSK, and you rarely hear about 32 PSK because you have to be in the circle, whereas 32 QAM, 64 QAM, 128 QAMs are well known. So just a graphical feel for the signal constellations for Emery QPSK. On the left hand side it should be Emery PSK, and on the right hand side Emery QAM. Please note here, the more points I try to fit in, I constrained myself. Here clearly all of them have equal amplitude, but here as you can see the 16 points are located here and they are less densely packed, hence the probability of error will be better in this case. Now just let us talk about the bandwidth and power efficiency for quadrature amplitude modulation. The first row represents m for the Emery QAM. What is interesting is that you start with 4, 16, 64 and go right up to 4096. Such numbers are unheard of for FSKs and PSKs. Now what is eta b? It is RB over B star. B star is the first null bandwidth, and here the EB over N naught required for bit error rate equal to 10 raised to minus 6 is also listed. So you can compare and find out and predict the bandwidth efficiency for a certain performance. This is a simple example which tells us that how the waveform of a QAM for m is equal to 16 will look like. So if I have the two axes, the x and the y axis, and the data is coming as a combination of these two, then you have the real and imaginary waveforms looking like this, and when you add it up, the complex waveform looks like this. So the point to be noted is that there are clearly 4 amplitude levels and the phases can also vary, hence the name quadrature amplitude modulation. Now we move on to another method called the spread spectrum technique. What is spread spectrum? Spread spectrum is a special modulation technique that spreads the transmitted signal over a frequency range much wider than the minimum bandwidth required to send the signal. For the first time, we are trying to be greedy in terms of bandwidth, but we know from Shannon's theorem that if we have to invest, it is better to invest in bandwidth than increasing your signal to noise ratio, because the capacity of a system grows linearly with bandwidth and logarithmically with SNR. So it intuitively follows from the Shannon's theorem that it is better to have a larger bandwidth and send noise-like signals. Here we wish to exploit that fact, and the frequency range which will actually be used for transmission will be much more than the signal bandwidth. What else does it do? Widening the signal bandwidth in this fashion increases the probability that the received information will closely match the transmitted information. There are two basic types of spread spectrum modulation techniques. The first one, and probably the more popular one, is the direct sequence technique. The other one is frequency hopped technique, which was fairly popular in the military domain and now has come out in the civilian applications as well. But the more common is the direct sequence, DSSS. Now, to do spread spectrum techniques, you have to have something called as pseudo noise sequences or PN sequences. A binary sequence with an autocorrelation that resembles over a period the autocorrelation of a random binary sequence is called the pseudo noise sequence. It is usually generated using a sequential logic circuit. One example could be as follows. So you have various stages. These could be flip-flops, and then there is a feedback logic, simple XORs, and then you output a PN sequence. How you tap these points depends on what kind of sequence you get. Now let us talk about direct sequence spread spectrum, also known as DSSS. The received spread spectrum signal for a single user can be represented as follows: S subscript SS T, SS stands from direct sequence spread spectrum, under root 2 ES over TS. Please note a product MT PT cos 2 pi FCT plus theta. In the subsequent slides, we will talk about what does this MT represent, what does the PT represent. This is of course a normalizing factor. MT here is the data sequence. PT is a PN pseudo noise spreading sequence. FC here is the carrier frequency, and theta is the carrier phase angle at time t is equal to 0. This is a general depiction of the received spread spectrum signal for a single user. We will soon see that the spread spectrum technique is very popular for multi-user scenario, where different users will have different PN sequences as the spreading codes. So let's start with the received waveform ST as MT times PT times cosine 2 pi FCT plus theta normalized. Let's talk about MT in a little bit more details. MT is a data waveform. It's actually a time sequence of non-overlapping rectangular pulses. Now please note that the amplitude is +1 when I want to transmit bit 1 and -1 when I want to transmit bit 0. So it's a bipolar depiction. The time duration is T of S. Let's now talk about this PT. PT is interesting. It is called a chip. Chip is much narrower in time than the bit, and this chip is actually causing the bandwidth to extend. The data waveform is a time sequence of non-overlapping rectangular pulses, and amplitude of +1 and -1 is used for PT as well, but the time duration Tc for PT is much smaller than Ts for MT. So, you will have several chips in one bit interval. Now, let us look at the block diagram of the transmitter for the case of direct sequence spread spectrum. Suppose I get a message MT, clearly it is bipolar, switching between +1 and -1. And then you have a pseudo random noise code generator, PN code generator, and a chip clock which makes it run. Combine them together, pass it through a baseband oscillator. This should be a product. So, message is multiplied with a PN code generator, pass it through a band pass filter, put it through an oscillator and send out your transmitted signal. This is the block diagram. Now, let us move over to the receiver end. The received direct sequence spread spectrum signal at IF is first fed into the IF wide band filter. Please note that the signal received is a wide band signal even at the IF. Here again we have a synchronization system which gives feedback to the PN code generator. Now, you should have the same code that was used to spread the message signal to despread it. If you use the same code, you despread your signal. If you use a wrong code, then you spread it further. You multiply it. The moment you despread it, the bandwidth reduces and now it is an IF narrowband signal. Now, you can do detection and obtain the received data. Here we can have either the coherent phase shift king or differential phase shift king demodulator. Now, let us see how does the spectrum of the desired received signal look like with respect to the interference. Suppose I have, this is my signal, x axis denotes the frequency, the y axis denotes the spectral density, and suppose I have an interference. Clearly, I am depicting a narrowband interference. It could be a jammer. Now, at the receiver, when you have the correlator, when you despread the signal despreads, its bandwidth reduces, but at the same time the interference gets spread. Since the power is constant, it is at a much lower level like this. So, this shows that a strong interference to a weak signal once despread gives you a strong signal and a weak resultant interference. In fact, this is the processing gain. Very simple technique, but very effective. What it also tells me is that I can increase my processing gain more and more, thereby will be able to handle stronger and stronger interferers or jammers. So, inherently this technique is secure against jamming to some extent. What is processing gain? Processing gain is defined by Ts over Tc. Remember, Ts is kind of the bit duration, Tc is the chip duration, which is much smaller than the bit duration, and it is written as Rc over Rs is approximately equal to W bandwidth RSS over 2Rs. Now, let us look at the other kind of spread spectrum technique called frequency hopped spread spectrum technique. The set of possible carrier frequencies is called a hop set. So, the whole philosophy here is as follows. You have a large spectrum, you subdivide it into subbands and you hop on these subbands. That is, you pick one of the subbands randomly or as per a pseudo noise random number generator and transmit it, and then pick another subband and then transmit it on that subband, and so on and so forth. So basically you jump or hop along the frequency spectrum across the different bands. The hopping occurs over a frequency band that includes a number of channels. What are these channels? These are frequency subband channels. The bandwidth of a channel used in the hop set is called the instantaneous bandwidth, WSS. The bandwidth of the spectrum over which the hopping occurs is called the total hopping bandwidth, B. So clearly there is a big large chunk of bandwidth, and then there are subbands which are narrower, and we are jumping and picking and choosing the different subbands. If only a single carrier frequency, that is signal channel, is used on each hop, the digital data modulation is called a single channel modulation. The time duration between hop is called the hop duration or hopping period, TH. So these are some of the definitions related to FHSS. The processing gain for FHSS is WSS over B. Let us now look at the transmitter for a frequency hopped spread spectrum system. So you have a data coming in, goes to a modulator, an oscillator input gives you this data. Now the question is, on which of the subband, which channel must it be sent? So you have a code clock which generates a PN code sequence, and then according to the PN code sequence you generate the frequency, up convert and send. So as I jump along my PN code, I jump along my frequency band. The PN code tells me which subband to choose for onward transmission. Let us look at the receiver for the frequency hopped spread spectrum technique. You have the frequency hopped signal coming. I have to pass it through a wideband filter, right? So I need something which is broad wideband at the RF. Now again I must have a synchronization system, and I must use the PN code in order to synthesize the same frequency. I multiply, pass it through a band pass filter and demodulate it. If I use a wrong frequency, I will get junk data. So it is important that the hopping sequence be the same, and hence we are getting a processing gain thereby. Now what are the different types of frequency hopped spread spectrum systems? There are basically two classes. One is the fast frequency hopping technique and the other one is the slow hopping technique. Fast frequency hopping occurs if there is more than one frequency hop during each transmitted symbol. That is, while I am transmitting my symbol, within the symbol duration I have already hopped several times. It is called fast hopping sequence. Thus the frequency hopping implies that the hopping rate equals or exceeds the information symbol rate. On the other hand, in the case of slow frequency hopping, I send several symbols over the same frequency and then hop at a later time. Clearly synchronization is an issue in the fast hopping case. Now spread spectrum techniques have become very popular for the code division multiple access technique, where multiple users can be supported by giving them different orthogonal or pseudo orthogonal codes. Let us consider the case when we have k users in the system and how they can use the CDMA, which is the direct sequence spread spectrum technique. So here I have message 1 emanating from user 1. User 1 has his or her own PN code, multiplied with the cosine 2 pi fct plus phi 1, you get your signal S1. Similarly, for M2, so and so forth till the kth user Mk. Take the signal, these are the bits coming in, multiply with the PN sequence, multiplied with the cos 2 pi fct plus phi k, you have the Skt. These are the time delays, summation, and this is the received signal. So, at the receiver, I have a summation of all these signals coming in. This is a multi-user scenario. What you want to do is extract, say, user 1's data and reject M2, M3 up to Mk. Right? So, you have to treat the other ones as interference. How does the receiver look like? So, let us talk about just receiver number 1, which is a summation of all the various kinds of messages being spread differently by different PN codes added together with a delay that is coming in. You take that and you multiply with user 1's PN sequence. What will happen is only user 1's sequence will despread and the rest other ones will spread even further. So, you go on, this is the despread signal, multiply, pass it through the band pass filter or integrate and dump and take a decision to get the received signal. So, a fairly simple receiver structure is a selling feature of CDMA systems. Let us now spend a few slides on the performance of direct sequence spread spectrum technique. What is that assumption? K multiple users. So, each user has a PN sequence with n chips per message symbol period t, such that NTC is t. Thus, the transmitted signal of the kth user can easily be expressed as follows. We have seen this expression before. For the it is the kth message and the kth sequence p subscript k t, and the other things remain the same, cos 2 pi fct plus phi k. Now, the decision variable for the ith transmitted bit of user 1 is given as follows. This is the summation of the different users, but this received signal is being multiplied by the PN sequence of user 1 with the proper time delay. This is obtained by proper synchronization. If you do not synchronize, you cannot recover your data. So, it is very, very sensitive to timing synchronization. Cos 2 pi fct again synchronized, phi 1 tt, integrate. So, this is the decision variable for the ith user. This can be written as Zi superscript 1 for the first bit user 1, ith bit I1 plus summation k is equal to 2 to capital K ik plus eta. What are these terms? In the next slide, let us understand what are these terms. Clearly and intuitively, I1 has something to do with the user's own despread signal. Here from 2 to k represents the interference due to the other users, and this is the omnipresent additive white Gaussian noise. So, we start with Zi equal to I1 plus summation k is equal to 2 through uppercase k ik plus eta. I1 is 0 to 2 S1t P1t its own sequence cos 2 pi fct dt. This is the response of the receiver to the desired signal from user 1. No problems. what is the other term? Here Ik represents the multiple access interference from user k. And this term is the Gaussian random variable representing noise with mean 0 and variance given by n naught t over 4. Here nt is the additive Gaussian noise. Fine. So if you calculate the average probability of bit error, it is given by Pe equal to Q function 1 over under root k minus 1 over 3n plus n naught over 2 EB. So please note that the k comes in the denominator with an under root sign. For the case when there is only one user, right? So it is not a multi-user scenario, but suppose you just want to communicate from point to point in the presence of a jammer. For a single user, k is equal to 1, and in the interference limited case when thermal noise is not a factor, EB over n naught tends to infinity. Under these constraints, the bit error rate expression has the value P is equal to the Q function under root 3n over k minus 1. This is coming from this term. Question?
Sir, this does not depend on the zeta factor. That is a previously we discussed.
Okay, the question being asked is, does it depend on the zeta factor? The answer is yes, it will depend on the zeta factor. Here the zeta depends on the additive white Gaussian noise and n naught is coming into the picture here. So this is n naught over 2 EB, it is 1 over SNR. So the signal to noise ratio is coming into the picture here. So please note that for large EB to n naught, this n naught over EB tends to 0, and you can directly get probability of error as Q under root 3n over k minus 1. Right. Please also note that if you put k is equal to 1 here, the first term vanishes, and you will have Pe is equal to Q under root 2 EB over n naught, the standard modulation technique, binary FSK. If two users are not simultaneously utilizing the same frequency band, the probability of error for binary FSK can be given by probability of error 1 over 2 e raised to the power minus EB over 2 n naught. When the hit occurs, the overall probability of bit error can be given as Pe as summation of two terms multiplied by the probability. One is half pH, and here 1 minus pH probability that hit does not occur. What is P subscript H? It is the probability of a hit. This has to be determined. It depends upon how many users are there in the system and various other factors. Now let us move to the performance evaluation of frequency hopping spread spectrum technique. If there are m possible hopping channels called slots, there is 1 over m probability that a given interferer will be present in the desired user's slot. If there are k minus 1 interfering users, the probability that at least one is present in the desired frequency slot is given by pH is equal to 1 minus 1 over m k minus 1. For large value of m, you can do a simple Taylor series expansion. You get 1 minus k minus 1 and neglect the larger terms, and you get it as k minus 1 over m. This is the pH. Performance of frequency hopping spread spectrum. If you substitute pH into this equation, it gives probability of error as the following expression. Some basic mathematics. If k is equal to 1, that is, we have only one user, the probability of error reduces simply to the BFSK, binary FSK scenario. If on the other hand EB over N naught approaches infinity, the probability of error is given by half k minus 1 over m. The previous analysis assumes that all users hop their carrier frequencies synchronously. Okay. This is called slotted frequency hopping. All of them are changing between one subband to the other subband at the same time. During the course of changing, they may land up using the same slot, and that's when they interfere. That is the probability of a hit. However, for the asynchronous case, the probability of a hit can be shown to be this quantity. Here NB is the number of bits per hop. The probability of error for the asynchronous frequency hopping spread spectrum case is given by a following expression. So they are pretty logical to follow from one step to the other. So we have an expression for the synchronous case, and here is an expression for the asynchronous case. In this case, two users can hop independently also in between the transmission. Let us now talk very briefly about the advantages and disadvantages of spread spectrum techniques. First, the advantages. First of all, they are inherently very difficult to intercept for unauthorized persons. We use a large spectral bandwidth, but the power emitted is very low. In fact, in CDMA systems, we only transmit as much power as required and no more. Very good power control is inherent and is compulsory for successful operation of CDMA systems. If we don't, then there is a fear that you will drown out other users. You will cause so much interference that other users cannot be heard. But in general, they are very difficult to intercept. The other advantage, they are easily hidden. For an unauthorized person, it is difficult even to detect the presence in many cases. They almost operate at the noise floor. Therefore, the advantage with military systems. Resistant to jamming, we have seen. Okay. It despreads its own signal but spreads further the jamming signal. In frequency hop case, if you are jamming in a certain band, you hop to the next band and you don't have any more problem with jamming. It provides a measure of immunity to distortion due to multipath propagation. So it is inherently wideband, usually more than the coherence bandwidth of the channel. So by definition, it is resistant to multipath fading to some extent. It also has an asynchronous multiple access capability. In fact, the multiple access property of the spread spectrum system makes it so popular today. Of course, no free lunch. There are some problems that come with direct sequence spread spectrum. The most important problem is the near-far problem. The problem is that all of the users are separated using their own codes. So consider, for example, the CDMA scenario where user 1 is closer to the base station and user 2 is farther away from the base station. In that case, the signal coming from the user 1 might drown the signal coming from the farther located user 2, unless user 1 closer to the base station lowers its radiated power. This is called the near-far problem. So without careful power control of each mobile users, so we are talking about a mobile, most likely the CDMA situation. In case of the mobile scenario, without careful power control, one user which is close in may dominate the received signal energy at a base station, making the Gaussian assumption inaccurate. Okay. Stronger signals may bleed into the weaker signals due to imperfect filtering. If that happens, we are forced to use strong error correcting codes like Reed-Solomon to overcome this problem. So, this is one of the biggest impediments. So, let us now summarize today's lecture. We started off with Emery-Quam, then we graduated to the PN sequences and the direct sequence spread spectrum technique as well as the frequency hopped spread spectrum technique. We looked at both these techniques in greater detail. We then analyzed the performance of direct sequence spread spectrum, followed by the performance of frequency hopping spread spectrum. In the last couple of slides, we looked at the advantages and the disadvantages of spread spectrum techniques. We will conclude the lecture here today. Thank you.